Today we're going to be working on AP Calculus AB FRQ from 2008, question number 5. And in this FRQ, we are given the differential equation dy dx equal to y minus 1 all over x squared, where x is not equal to 0. So we have dy dx equal to y minus 1 all over x squared when x is not equal to 0. So this is the equation of the slope of our function, and we are asked to graph the equation provided right here, which is the equation of the derivative with the graph that is provided to us. Now, in graphing differential equation, we need to understand the behavior of the slope when it's negative, when it's positive, when it's 0, and when it's undefined. So let's go ahead and write out the slope and how it behaves. So if the slope is positive, its behavior will be increasing, so the slope will can be illustrated as such, and negative can be represented by this line right here, and horizontal slope is a 0 slope, so that means it's going to be a horizontal line. And for an undefined slope, which happens when the denominator of your slope is 0, is going to be a vertical slope. So these four behavior of our slope is what we are going to be using in representing the graph of a differential equation. So let's start with the first line right here, which is an x value of -1, and the y value is changing at 0, 1, 2, and 3. So to organize the slope of our column 1, let's write x right here and y, and let's solve for the slope for each coordinate in column 1. So in column 1 we have -1, so it's not going to change, it's going to be -1 for all three function right here, because we're just graphing values from 0 up until 2, so we don't need the 3 anymore. So this is going to be at y equals 0, y equal to 1, and y equal to 2. Now to find the slope, we are going to use the equation of the dy dx, which is y minus 1 all over x squared. So since our x value is consistently at -1, we know that the first slope will have -1 squared, which is just going to be +1. So by observation, if y is equal to 0, 0 minus 1 is equal to -1. Therefore, our first slope is going to be a negative number, which is -1. And if y is equal to 1, if we plug it into our dy dx, it's going to be 1 minus 1, which is 0. 0 over 1 is 0. So the slope is 0 at x equals -1 and y equals 1. And for the third iteration, if y is equal to 2, 2 minus 1 is +1. So 1 all over 1 is +1. So we have a negative slope, a 0 slope, and a positive slope at y equal to 2. So if we're going to graph it in our space right here, at y equals 0, it's a negative slope, so this will be the behavior of our slope field for the first item right here. And then at y equals 1, it's going to be a horizontal slope because the slope is equal to 0. And for the third coordinate, we'll have a positive slope, so this will be the behavior of our slope field for the next column. Now for the second column, which is at x equal to 0, we know that x equal to 0 is going to be undefined. So if it's an undefined graph, that means all our slope fields will just be a vertical line. So we don't even need to use our table right here. We know that it's going to be undefined. So we have all vertical lines for column number 2. For column number 3, which is at x equal to 1, so we have 1, 1, 1, with y values at 0, 1, and 2, and then we're going to look for the slope. Now, with the equation of y minus 1 all over x squared, we'll have 1 squared giving us a positive 1 in our denominator. So just like the behavior of x equals negative 1, our x equal to positive 1 will share the same result for the slope. So this is still going to be negative 1, 0, and 1. Since if you plug in 0 to here, it's going to be negative 1 all over positive 1, which is negative 1, and 1 minus 1 is 0. 0 over 1 is 0, and so on. So we're just going to have these behaviors. So at y equals 0, it's negative. So at y equals 0, the slope is negative. At y equals 1, it's horizontal because the slope is 0. And at y equals 2, it's going to be a positive slope. Now for the third line right here, or actually the fourth line, which is at y equal to 2. So we have x, y, and m. And we'll have 1, 1, I'm sorry, it's supposed to be 2, 2, 2. And the y values will be 0, 1, and 2. So we have y minus 1 all over x squared. Our denominator now is going to be 4 because 2 squared is 4. So let's just leave our denominator right here because we're going to start plugging in the value of y to our equation to see what our slope will be. So if 0, or if y is equal to 0, 0 minus 1 is negative 1/4. 1 minus 1 is still 0, so this is 0 over 4, which is 0. And 2 minus 1 is going to be 1, which is positive 1/4. So since we have a negative slope, 0 slope, and positive slope, the behavior of our slope field will still be the same as the other or the previous slope fields that we had. But if you want to be a little bit more precise, we know that 1/4 is closer to 0, so that means our slope will be less steeper than the previous slopes right here. So for the first one, at y equals 0, we have negative 1/4, so we can have a negative slope, but it's going to be a little bit closer to 0. So we can have a slope like that. So from this, it will become a little bit slanted like that. And for y equal to 2, at x equal to 2, it's still going to be a horizontal slope. And for x equals 2 and y equals 2, it's still going to be a positive slope, but it's going to be less steeper than the other one, or the other two graph right here. So that is the graph of our differential equation using slope fields. Now let's go ahead and start answering problem letter B. For problem letter B, we need to find the particular solution of y equals f of x. So we need to find the function f of x given the dy dx. And the initial condition is that f of 2 is equal to 0. So we need to find the value of our function f of x given the dy dx, which is y minus 1 all over x squared. So here we are going to set up our function to find y equals f of x. So we need to separate our function and perform separable equation to integrate our function so we can find y. So let's rewrite it. This is letter B. dy dx is equal to y minus 1 all over x squared. So we're going to group the dy's together and y, and group the dx together. So by cross multiplication, y minus 1 will go over here, and dx will go on the other side of the equation. So our equation will be dy all over y minus 1 equals dx all over x squared. Now to make it a little bit easier to integrate, so let's change our function or modify the function into 1 all over y minus 1 dy equal to the integral of 1 over x squared dx. So the antiderivative of 1 all over y minus 1 will be ln, absolute value of y minus 1, equal to the integral of x to the negative 2 dx. So we know that the antiderivative of x to the negative 2, you add 1 to the exponent, so it becomes negative 1. So we have ln of y minus 1 equal to x to the negative 1 all over negative 1 plus c. So we can rewrite x to the negative 1 all over negative 1, so it will become a little bit easier to solve. We'll have negative x to the negative 1 plus c. So to have y by itself, we can raise both sides to e, so we can have, or we can get rid of ln. So multiplying both sides by e, we'll have e to the ln y minus 1 equals e to the negative x minus 1 plus c. So e raised to ln will have y minus 1, and now we have e raised to the negative x to the negative 1 plus c. By using the law of exponent, we know that if we have x to the m multiplied by x to the n, it's equal to x raised to m plus n. So using the law of exponent, so we are given x raised to m plus n, we can rewrite e raised to negative x to the negative 1 plus c into a separate term right here using the law of exponent. So we can have e to the negative x to the negative 1 multiplied by e raised to c. So we can have our constant here and change it into k. So now we can have our general solution as y minus 1 equal to e to the negative x to the negative 1 multiplied by the constant d. So to have y by itself, we have y equals e to the negative x minus 1, or raised to negative 1, multiplied by d plus 1. So this is our specific solution, and now all we need to do is to find the constant d by plugging in the initial condition, which is at f of 2 equal to 0. And f of 2 equal to 0 means the x value is 2 and the y value is 0. So by substitution, we'll be able to find the constant d in our differential equation a while ago. So here we'll have 0 equals e to the negative 2 to the negative 1 times d plus 1. So by simplifying e raised to negative 2 to the negative 1, we can have e raised to negative 1/2 times the constant d plus 1, which gives us negative 1 equals e to the negative 1/2 times d. And to have d by itself, we divide both sides by e to the negative 1/2, e to the negative 1/2. So this cancels out. So d is equal to negative e raised to positive 1/2. So this is our constant d that we solve using this algebra work that we just finished. Now that we have the constant d, now we can solve for the function f of x by rewriting our equation. So we have our y value right here, our general solution, and to find y equals f of x, all we need to do is to replace d by negative e to the 1/2. Let's rewrite it. So we know that our general solution is at y equals e to the negative x to the negative 1 multiplied by d plus 1. We know that the constant d is equal to negative e to the 1/2. So to write our particular solution, all we need to do is replace d by negative e to the 1/2. So we'll have y equals e raised to negative x to the negative 1 multiplied by negative e raised to 1/2 plus 1. And if you want to simplify this further, we can combine the two e's right here. So we'll have y equals e, or negative e, raised to negative x to the negative 1 plus 1/2 plus 1. And this is our particular solution, which is what we're looking for question letter B. Now for question letter C, we're supposed to use the particular solution, y is equal to fx, and find limit of f of x as x approaches positive infinity. So our particular solution is y equals negative e to the negative x minus to the negative 1 plus 1/2 plus 1. And we're supposed to solve for the limit of f of x, which is this function, negative e to the negative 1 over x plus 1/2 added to 1 as x approaches infinity. So I modified my x raised to the negative 1 to 1 all over x, so I can easily evaluate my infinity or x at infinity right here. So by substitution, negative e raised to 1 over infinity plus 1/2 plus 1. We know that 1 over infinity is equal to 0. So our limit of f of x as x approaches infinity is simply negative e raised to 1/2 plus 1. And this is our limit, which we can rewrite as square root of negative square root of e plus 1. So this is how we answer problem letter C on the 2008 FRQ question number 5.